slower than 100 or 010 or 001 plane. 100, 010 and 001 plane is nothing but all the faces of a cube, and 110 is the edge of the cube. See, edge of the cube, if you cut, the plane that is generated is 110. That plane should grow slower so that it survives. So if I can create a situation that all the 110 planes survives, that means all 12 planes, this 100 plane, that is the original plane of the cube, will disappear. Right? So aage gele bage khaye, pore gele sona paye. Keep that in your mind. So this is shown in this schematic, animation. So suppose this is a crystal, it grows. Yeah. So another layer comes, It retains its shape because all the planes are growing at the same rate. So at the end of the day, you get the same shape. But if a situation is something like this, suppose this is your crystal, the next one is like this, next one is like this. What it means that this particular plane is growing faster, so disappears. At the end, it does not exist. But this particular plane is growing slower than this one, that's why they survive. So starting with a crystal having 1, 2, 3, 4, 5, 6, 7, 8, you end up getting 4 sides. Now look at this video. So this is called invariant growth, this is called overlapping growth, and fastest growing phase disappears. Now look at this video. I hope it works. Yeah. Particularly look at this particular place. You see? This is nothing but sodium chloride. And this particular plane and this particular plane are growing very fast. And you see, at the end what happens? See, they don't exist. So this is a video we have taken in our own laboratory during that period to see how sodium chloride grows. So this is one of the examples I always demonstrate to students to make them convinced, aage gele bage khaye, pore gele shona. Correct? Now, this morphology modification, that whatever I have talked about is morphology modification or habit modification, you can achieve by various ways. Rate of crystallization, degree of super saturation, temperature, pH of the solution, and impurities. I have already given you this example of impurities that was, demonstrated many 100 years ago, that sodium chloride can be octahedral if you crystallize it from urea. It was crystallized from urine, urine contains urea, and urea was the impurity. Later on it was established. So I'll give you some example of habit modification of some other, taken from the literature. For example, if you take succinic acid, if you crystallize it from water, it gives you this kind of shape, but if you do it from isopropanol, it gives you this kind of shape. Sodium chloride, usually cubic, but if you do it in presence of cadmium chloride, it's called chemisorption, it's no more sodium chloride, it contains cadmium chloride and sodium chloride and water, it gives you octahedral. Urea, suppose this is the size of the urea, but because of the impurity present, called biurea, the growth retards. This is biurea. And because of hydrogen bonding, this is urea, okay? And because of the hydrogen bonding, this growth in this side is retarded, and therefore crystal become, shortened. Another example, the crystallization of benzamide. Benzamide, if you crystallize in presence of benzoic acid, 2-methyl benzamide and 4-methyl benzamide, you have various kinds of effect on the crystallization. I think it will be little bit too much for students of 11 and 12, so I will skip this slide. Just to tell you that because of this hydrogen bonding involved by this kind of impurity, this crystal shape changes. So I will skip this. This is very important. Ammonium sulfate. Pure ammonium sulfate looks like this, but in presence of 5 ppm chromium, the shape changes. If you increase chromium concentration, shape further changes. So these are all known in the literature. Sodium chloride. This is sodium chloride. Who will believe this? This is sodium chloride. This is called dendritic growth. It is done in presence of 1000 ppm of potassium ferrocyanide. This is done in my laboratory. I have taken this photograph. Okay? So it is very important because sodium chloride growing like a dendrimer, it actually bulk density reduces. So this is used now. If you take the sodium chloride and crush it, it is, first of all, it is not taking, it is free flowing, and bulk density is less, and therefore you can use it for sprinkling on the road where you have lot of snow. But obvious reason, because no drug and food administration will allow you to use potassium ferrocyanide because of the obvious reason. So this is all known in the literature. Now, when I started this project, we read some literature and found out that if you have a saturated solution of sodium chloride, for that matter anything, so saturated, and then you add something in it which is very much soluble to that solvent, it will salt out, rather crystallize out the major part. So it's called kind of forcing nucleation and forced crystallization. So we did this experiment one day, and you can see this is the crystal of sodium chloride. They are all round. Most of them are round, looks like a pearl, transparent. How we did that? We took a saturated solution of sodium chloride and we added ethanol. Ethanol is very much soluble in water, and therefore it immediately kind of kicks out sodium chloride from the solution. It does not have enough time to grow properly to give you the cubic crystal, and as a result you end up getting this. So we said, we have solved the problem. Very happy. But it was kind of an accident. We did it crudely. I did this experiment along with my student. So I took a beaker, sat in front of the microscope, added ethanol, like a shower. You can do this experiment in your laboratory also. It's a very simple experiment. You see that sodium chloride will just come like this. You can see the crystal forms. Immediately I put under the microscope and I saw this. And I told my student, project is over. But then, that's not over. You have to tell exactly how much ethanol you have to add. And when we did this experiment, went back and did this experiment systematically, not reproducible. Only once we got it. It is true, but it is not reproducible. We could never reproduce it. So we did hundreds of experiments. Then finally we thought, okay, this is not the way. We gave up. Then we tried other things. We tried many things actually. Hundreds or thousands of experiments. So we used magnesium chloride, all arbitrary. Potassium bromide, potassium chloride, magnesium sulfate, calcium sulfate, what not. We did like seed crystal, we took cubic crystal and put it in sodium chloride solution and added some impurity, all kinds of things. And this is some of the photographs that I have shown you. You can see that nothing much happens. You see that there are some cavities we saw. Initially we were excited, okay, we created sodium chloride with a cavity. But later on we found out literature, this is quite common. So we gave up, got more frustrated. Then we started using all kinds of amino acids because amino acids, as you know, they exist in deuteronic form. So it has got a polar, plus and minus, sodium chloride also plus and minus, so we thought some kind of interaction may take place. We did all kinds of, study, and mostly we got cubic crystal, as we can see, with this kind of concentration. So long table, I skip. Then one day we found this paper. 1949, somebody reported that if you use glycine, then you get a crystal of sodium chloride which looks like rhombic dodecahedron. And this is what we wanted. We did not know about this paper when we did all kinds of other things. But finally we could see this paper, and then we went back and we read the paper in detail. So it is only just a report saying that sodium chloride gives you rhombic dodecahedron and nothing else. It does not even say that how much glycine actually you have to add. So we thought, okay, let us do this. So this is rhombic dodecahedron, as I said. You can see it has got 12 face and all faces are rhombus. Okay, and this is all the faces here is 1, 1, 0, or it's different kind like -1, 0, and so on and so forth. And this you can do it from, as I said, by chopping the H. So the report says glycine. We took the crystal structure of sodium chloride, solved many years ago by Braggs, and we used glycine here. This is glycine crystal structure, and this is the supramolecular arrangement of glycine through hydrogen bond. You can see that. And this is, sodium, and this is carboxyl. So they can interact in this fashion. So in this direction, if you see 1, 1, 0, it is alternately sodium and chlorine. And therefore we thought probably this is the way glycine is actually binding to 1, 1, 0 phase, and therefore not allowing the phase to grow faster than 1, 0, 0. As I said again, the rule, aage gele bage khai, pore gele sona khai. So therefore glycine is doing the job. Glycine is just kind of binding to 1, 1, 0 surface when the crystal grows, and this particular surface is growing slower than the other phases. As a result, at the end of the day, what you are getting is rhombic dodecahedron. So schematically I show that here. You chop the edges, what you get is this, right? And then finally you get rhombic dodecahedron. And this is not, this is not hypothetical. We have the evidence. You can see that age modified, crystal of sodium chloride. What we did in this case, we took a seed crystal of cubic crystal, put it in saturated sodium chloride solution containing glycine, and we end up getting this crystal. You see that? You can exactly, match with this, the edges. So 1, 1, 0 plane is very much seen here. I can show you a better picture later. So what is the minimum initial concentration of glycine required to in saturated brine to affect the modification? So we had to do a systematic study. And what is the effect of temperature on the process? This information is necessary since crystallization temperature are very different for solar salt production and forced evaporative crystallization. So ultimately, if you have to apply this concept in real life, you have to add glycine in the reservoir in the open space, and their temperature is about 40 degrees. So you have to know whether at that temperature it works or not. So we have done all these studies, and we have found that when the concentration of glycine is about 25%, then you get rhombic dodecahedron. Actually, rhombic dodecahedron starts to form around 23 to 25. So we thought 25% is the safest. So around 25% of glycine is required to, to see the effect. So this is the modified crystal. This is not rhombic dodecahedron, just previous stage. This is a sodium chloride crystal. You can see that all edges are seen. This is 100 plane and this is 110 plane. So this plane is growing slower, this is growing faster, so it disappears, it retains, and as a result at the end you get rhombic dodecahedron. So these are the examples. You can see very nice crystal of sodium chloride. This is a scanning electron microscopy of the rhombic dodecahedron crystal. You can see very easily this rhombic crystal here. And at temperature 50 degrees centigrade, you have mainly cubic crystal. 80 degrees centigrade, only cubic crystal. So with temperature, this effect is not very good. That is probably of the kinetic energy. Probably glycine is not able to bind efficiently with because of the lot of heat. So, but at 40 degrees centigrade in solar evaporative condition, this is working fine. Absolutely no problem. So now the practical problem is when we took this result to Hindustan Liver, they said, oh my God, 25% glycine. So that is too much. This will not be commercially viable. So we have to solve this problem. How can we recycle glycine? So that was a big problem. Why? Let me tell you how we were doing this experiment. We used to take 25% glycine required for a given volume of solution. So add that, take water and then add sodium chloride, make it saturated. So as a result, 25% glycine remains there, and when you crystallize it, along with your rhombic dodecahedron sodium chloride, glycine is also coming out. So you have to separate it. That was a big problem. So in one such experiment, we thought in a different way. What we did, we first make the saturated sodium chloride solution, which is completely saturated, and then we added the amount of glycine required solid in it. To our surprise, all went into the solution, which we never expected. We are not physical chemists, we are not theoreticians, we are not crystal growth person, so we could not explain this, but this is a fact. And that actually gave us the edge. Because now, what you can do, you know that saturated sodium chloride solution can actually dissolve glycine. So in first batch, when the crystals comes out, you have the sodium chloride and glycine. You add saturated sodium chloride solution into it. Sodium chloride will not be dissolved, but glycine will be. So as a result, by doing this wash, you are getting the rhombic dodecahedron crystal separated. And again, about 25% glycine is present in your next batch. And by this way, in batch crystallization, it was possible to solve this problem. We could convince Hindustan Liver. So this is schematically shown.